Welcome. So in this differential equations tutorial, we are going to introduce you to partial differential equations. So most of these will be fairly easy examples. Like for example, in the first one, we're verifying that a function satisfies a PDE, and then eventually we will learn how to solve some of these differential equations. Okay, so let's begin with the first one. Question 1 says we have a function u, a function of x and t, 55 plus 22x to the power of 6 plus x to the 12th times sine of 2t. And so we want to take derivatives of this. So let's begin with u subscript t. And so this is the partial derivative of u with respect to t. And so differentiating this partially, this function of x in front can go right through the differential operator. And so we differentiate sine of 2t with respect to t. Now that requires the chain rule. But what it does is it multiplies by the derivative of sine, which is cos, multiplies by 2, the derivative of 2t with respect to t. So we end up with an extra 2 here. So 2 outside of 55 plus 22 x to the 6th plus x to the 12th cos of 2t. Okay, so this is u subscript t. Now u subscript tt is the second derivative partially of u with respect to t. So we just differentiate this again. Now, again, this is a function of x in front, so that can float through the differential operator, and we just differentiate cos of 2t with respect to t. Now, the derivative of cos is minus sine, so we end up with minus the derivative of 2t with respect to t is 2, so 2 times 2 is 4, so minus 4, 55 plus 22x to the 6th plus 12, x to the 12th sine of 2t. Okay, now u subscript x, this is the partial derivative of u with respect to x. And so we differentiate this function of x here, letting that sine of 2t float through the differential operator. So then we have sine of 2t times the derivative with respect to x of 55 plus 22 x to the 6th plus x to the 12th. Okay, now differentiating that polynomial there, we have 22 times 6 is 132 x to the 5th plus 12x to the 11th. So this is our ux. uxx is the derivative of this with respect to x. So in other words, differentiating again. And so we have sine of 2t times the derivative of 132x to the 5th plus 12x to the 11th. So 5 times 132 is 500 plus another 160, so 660 x to the 4th, and then 12 times 11 should be 132, so x to the 10th. Okay, now we need to calculate u xtt. And so what this is the second derivative of ux with respect to t. So we look at this line and differentiate that with respect to t, and then we do that again. Or sorry, this line. And so the derivative of sine is cos, but we use the chain rule and pull out an extra 2. So 2 cos of 2t, 132 x to the 5th plus 12x to the 11th is our first derivative of that. So we need to differentiate this again. Okay, and so we can pull the 2 and this polynomial function of x out in front and differentiate cos of 2t with respect to t. We get minus sine. but then multiply by the derivative of 2t with respect to t, and so an extra 2 comes out, and so we get minus 4 sine of 2t times 132 x to the 5th plus 12x to the 11th. Okay, so now we need to expand putting the minus 4 inside, because we're going to add this result here times x to the 5th to 12x to the 4th plus utt. Okay, so let's just begin here by writing 12x to the 4th utt minus x to the 5th uxtt. This is equal to, now where is u double t? It's up here. So multiplying this by 12x to the 4th. Okay, so then we have minus 48 for 12 times 4. Then I'm going to put the x to the 4th inside the bracket. So I'll have 55 x to the 4th plus 22 x to the 10th plus x to the power of 4 plus 12 is 16. Sine of 2t for this term. Okay, now for minus x to the 5th uxtt, we're looking at this line right here and multiplying that by x to the 5th. So minus x to the 5th times minus 4 gives us 4x to the 5th. So this is going to have a plus in front of it. So plus, and now 4 times 132 is 528. Okay, so 528 x to the power of 10, and then 12 times 4, 48, x to the power of 11 plus 5 is 16, sine of 2t. Okay, so it remains to expand this minus 48 into this polynomial and then add these two polynomials factoring out the sine of 2t. So doing that, minus 48 x to the 16th plus 48 x to the 16th, the two of those vanish. So now we need to calculate 48 times 22. So I'll open up Mathematica here. Okay, 48 times 22. So 1056 for that. So minus 1056 x to the power of 10. Okay, what is 48 times 55? 2640. So minus 2640 x to the power of 4. And then we have plus 528 x to the power of 10. And that's all times sine of 2t. All right, so finally, 528 minus 1056. Now, 528 times 2 is 1056, so this is minus 528. So we get minus 528 x to the power of 10 minus 2640 x to the power of 4 sine of 2t. Now, what is this? Well, it's meant to be equal to, according to the problem, it's meant to be equal to minus 4uxx. Let's have a look. If we take this line, multiply it by minus 4, this is exactly what we're going to get. We have minus 4uxx. And so we have verified that that function there satisfies the PDE in the PDF. Okay, question 2. A function is called harmonic if it satisfies Laplace's equation, which is this one, second derivative with respect to x of u plus second derivative with respect to y of u is 0. So this is Laplace's equation there. Now, if in question part A, u is 3x plus 4y plus 1, differentiating with respect to x, we just have 3 doing that again, uxx is 0, uy is 4, and uyy is 0. So yes, it satisfies Laplace's equation, uxx plus uyy equals 0. So u is harmonic. Okay, part B. We have a function u equal to e to the 3x cos of 3y. Now differentiating this partially with respect to x, we need the chain rule for this. This doesn't have any x's in it, so it comes through the operator. Differentiating e to the 3x with respect to x partially gives us 3e to the 3x, and then the cos of 3y just comes along. Okay, differentiating this again, uxx. Now we would need the chain rule on this one, so it brings down an extra 3. 3 times 3 is 9, so we get 9e to the 3x cos of 3y. Okay, now uy is e to the 3x times the derivative of cos of 3y with respect to y. Now we have cos goes to sine, cos goes to minus sine, so minus, and then 3 sine 3y. Okay, doing this again, we would pull out another 3. Derivative of sine is cos, so we end up with minus 9e to the 3x cos of 3y. Okay, and so now uxx plus uyy is this plus this, which is 0. So again, u is harmonic for this example. Okay, question C. We have u is equal to e to the 3x cos of 4y. Now, it's not going to work out this way this time because these are almost identical functions. The difference is this number. So what happens is we have something similar in uxx, but something totally different in uyy because the 4's keep coming out. So we end up with a 16 out the front for the uyy, but a 9 out the front for the uxx. So those are not going to add up to 0. So let's just say not harmonic. Okay, part D. U is the natural log, so I'll write ln here, x squared plus y squared. Okay, and so ux is using the chain rule, the derivative of x squared plus y squared with respect to x partially is 2x. We have 2x in the numerator, and then we have 1 over, so 1 over x squared plus y squared. Okay, so there is our derivative of u with respect to x partially. Now, differentiating that again, so uxx equals, we need the quotient rule for this, so we have 1 on v squared, now v being that denominator, and then v du on dx, so that's just 2 minus, and then we swap around the roles, u, which is 2x, times the derivative of v with respect to x partially, and so that is just 2x. Okay, so simplifying this, in the numerator, which is what we have in brackets here, we've got 2x squared minus 4x squared is minus 2x squared. And then we have 2y squared. And that's all over x squared plus y squared. All right, so there's a certain symmetry in here, you see, because if you change the name of x to y and y to x, you would have the same function. So then we know that uyy is going to come out to be equal to minus 2 y squared plus 2x squared in the numerator and x squared plus y squared in the denominator. So now if we add the two of these together, well, they vanish, right? Because 2y squared minus 2y squared is 0, minus 2x squared plus 2x squared is 0. So yes, this u is harmonic. All right, part E. So we have u equal to sine of e to the x cos of e to the y. Okay, so ux is, now we can ignore this and pull that out the front. So we have cos of e to the y times the derivative with respect to x of sine of e to the x. Now we need the chain rule for this. So differentiating with respect to e to the x, we would get cos of e to the x, but then we have to multiply by the derivative of that inside function, which is e to the x. So we have cos of e to the y times e to the x times cos of e to the x. Okay, now differentiating that again with respect to x, we have cos of e to the y times the derivative with respect to x of e to the x cos of e to the x. Now for this, we need the product rule and then the chain rule. Okay, brackets e to the x times the derivative of cos of e to the x, which is minus e to the x sine of e to the x. Okay, and then plus, and we swap the roles of these. So we have cos of e to the x times e to the x. Now we should really simplify this one. So there is a common e to the x that we can pull out. Okay, and then what remains is cos of e to the x minus e to the x sine of e to the x. Okay, now let's do uy. So we have sine of e to the x times the partial derivative with respect to y of cos of e to the y. So differentiating cos gives minus sine, but we also need to use the chain rule. So we have minus e to the y sine e to the x sine e to the y. Okay, now differentiating this again requires the product rule, just like we did above. So u yy is, now we will let that sine e to the x come out in front. Okay, let's bring the minus sign with that. And then we are differentiating sine e to the y, and then another e to the y in front of that. All right, great. So we need the product rule for this. So big bracket here. So e to the y times the derivative of sine of e to the y, which is e to the y cos of e to the y. And then plus, now we swap around. So the derivative of e to the y is e to the y. And then we have sine of e to the y. Okay, so we've used the product rule and the chain rule to differentiate this product. So now let's factorize. So what is common here? Just the e to the y. We have minus e to the y sine e to the x e to the y cos e to the y plus sine of e to the y. Okay, now comparing these two, well, I mean, to compare this properly, we really need to expand this, don't we? So let's see. This one has two causes in it, multiplying together. Does this one have that? No, it doesn't. It does have two sines in it. So the sum, we don't have to actually add those. We can see that it's not going to add up to 0. So u is not harmonic since uxx plus uyy will not be equal to 0. Okay, let's check this in Mathematica. Okay, so there's u. Now we want to differentiate u with respect to x partially twice. Okay. And then add to that the derivative of u partially with respect to y twice. Let's expand this. Okay, so we get 4 terms, and they don't vanish. So this is not harmonic. Doesn't add up to 0 in general. Okay, question 3. Find the general solution to the PDE u subscript x is cos of y if u is a function of x and y. All right, so what we need to do here is integrate both sides. So u of x and y is the integral of cos of y with respect to x. I write an ordinary looking d, but it's a partial integral because we had a partial derivative here. Okay, and so integrating this, we have x cos of y. We are treating this cos of y as a constant. And so the integral of k is just kx, but then we need a plus c. Now, it's not plus c here because the most general possibility is a function of the other letter. That is a partial derivative. So a function of the other letter, let's just call it g of y. Okay, and so notice we have this u and we take ux. What are we doing? We are differentiating x cos y with respect to x partially, and we are differentiating with respect to x g of y. All right, and so here the derivative of g of y, since that it's a function of y which has no x's in it, that derivative will be 0. And this derivative here, we bring out the constant, and so we're just differentiating x with respect to x, and so we just have 1 for the derivative times cos of y, which is cos of y. Okay, let's move on to question 4. Find the general solution to u subscript y is cos of y. Okay, now this one is a little bit different because when we apply the integral to cos of y, it's not just a constant this time, or not treated as a constant. So the integral of cos is sine. So we have sine of y, but we still have plus a function of the other letter. Okay, so that if we differentiate this partially with respect to y, we get cos of y for this, and we get 0 for this. All right, let's move on to question number 5. So in question number 5, we are given uy is 3, and we're given some boundary value. ux0 is 4x plus 1. Okay, so first we want to solve our differential equation. So u is equal to the integral of 3 with respect to y. And so we have 3y plus g of x. And now we want to use this information here to get what function g of x is. So we have u of x comma 0 is, now putting the 0 in for the y, we have 0 plus g of x. And we're told that this is 4x plus 1. So this gives us g of x is 4x plus 1, and so u of x and y has to be equal to 3y plus 4x plus 1. Okay, question number 6. We have ux is 2xy plus 1, and we're also given the initial value u of 0, comma y is cosh of y. Now remember what cosh is. Well, do I remember? I always seem to get the signs mixed up. So e to the y. I'll open up Mathematica and get a reminder on what cosh is by putting in cosh of 1.0 and comparing that to 1/2 brackets exp 1.0 plus exp minus 1.0. Are these the same? Yes. So that reminds me that cosh is 1/2 e to the x plus e to the minus x. But here it's cosh of y. Okay, and so now let's solve our differential equation. So u is the integral of 2xy plus 1 with respect to x. So integrating this with respect to x, we treat the y as a constant. So x squared y plus x plus a function of the other letter plus g of y. So that if we differentiate this partially with respect to x, we get exactly this up here. Okay, now u of 0, y, subbing in 0 for the x, we have 0 here, we have 0 here, we just get g of y, and so that's given by this. So that tells us g of y is this, and so then u of x and y is x squared y plus x plus cosh of y, which is just that. Okay, fantastic. Let's move on to question 7. Find the general solution to uxx equals 3. Okay, so integrating this with respect to x, we have ux is the integral of 3 with respect to x. And so that's 3x plus a function of the other letter, because we're told here that u is a function of both x and y. So the other letter here is y. Okay, now this is ux. So if we integrate this again, we have u as a function of x and y. The integral of 3x plus g of y with respect to x. So that's 3 over 2 x squared plus x g of y plus some other function h of y. Okay, so this is our most general solution to this partial differential equation. Question 8. Find the general solution to uxy equals 8xy cubed. U is a function of x and y. Okay, so remember uxy is ux differentiated again with respect to y. So we want to integrate this line with respect to y partially. So we get ux is the integral of 8xy y cubed dy. So integrating this with respect to y, we add 1 to the exponent of y, divide by the new exponent. So we have 8 over 4 xy to the power of 4, and then plus some function g of the other letter, x. So this is ux. Okay, now integrating this again with respect to x, this time, we're integrating 2x y to the 4th plus g of x with respect to x. Okay, so for this one, we're adding 1 to the exponent of x, dividing by the new exponent. So we have x squared y to the 4th plus some other function f of x, where f of x is the integral of g of x. And then since this is a partial, what's the other letter? It's y, so plus h of y. Okay, and so this is what u looks like in general, satisfying this PDE. Question 9. U x y x equals -2, and u is a function of x and y. Okay, so integrating with respect to x, we have uxy equals the integral of -2 with respect to x. So we get -2x plus some function f of the other letter, y. Okay, now integrating this line with respect to y partially gives us ux is -2xy plus some function g of y being the integral of f of y plus, what is the other letter? X. So plus some other function of x. So that if you take this line and differentiate partially with respect to y, this is what you get, this. All right, now integrating this with respect to x, we have minus x squared y for the integral of -2xy. We have plus x g of y, and then what comes after h? I, but that's a bad letter to use. So let's use k of x for the integral of h of x. And then we'll just use L of y. So that if we differentiate partially this line, we get the previous line. Or we get this. Okay.